Okay, get this. Imagine a robot that can 3D print enormous metal objects. I'm talking parts for a bridge, an airplane, or even a rocket, literally building it right in front of you. It sounds like something straight out of sci-fi, right? Well, it's not. It's happening right now, and the tech is getting faster and smarter by the minute.
But here's the catch, and it's a big one. When you're dealing with molten metal, trying to go fast it's really, really hard. So how in the world do you speed things up to build big stuff efficiently without the whole thing just turning into a lumpy, weak disaster?
Well, the answer lies in a process with a super technical name, COBOT WAM. Yeah, it's a mouthful, I know, but stick with me. It basically means you have a smart, collaborative robot, that's the COBOT part, doing a special kind of 3D printing with a metal wire and an electric arc. Just picture a super precise robotic welder building an object up, one layer of metal at a time. It's an amazing process for these huge jobs. All right, so here's where the plot thickens. In manufacturing, time is money, right? You gotta go fast to be productive. But, and this is a big but, when your main ingredient is a tiny pool of molten metal, just cranking up the speed causes some major problems. It really boils down to this classic trade-off. If you go slow, the metal lays down beautifully. You get strong, smooth, stable layers. High quality for sure, but it takes forever. If you try to speed up, the whole process gets chaotic, and you end up with weak, bumpy, unstable layers. And yeah, weak and bumpy is not a phrase you want to hear when you're building a part for a rocket. So what's actually going on here? Why does going fast mess it all up? Well, the research puts it perfectly. At high speeds, the molten metal actually creates a backflow. The best way to picture it is like trying to squeeze frosting out of a piping bag way too fast. It doesn't come out in a nice, smooth line. It just kind of bunches up and gets all wavy. And these ugly results actually have names. You can get something called humping, where the metal track looks like a series of bumpy waves, creating all these weak spots. Or you can get something even worse, disintegration. The name says it all. The track of molten metal literally just breaks apart into separate little blobs. It's a complete structural failure, an engineer's absolute nightmare. So that's the puzzle, right? How do you get speed and quality? You need both. And this is where the researchers came up with a solution that is so elegant and sounds so simple, it's almost funny. They just taught the robot a new move. The fancy scientific name is longitudinal oscillation, but let's just call it what it is. It's a wiggle, a very controlled, very precise back and forth wiggle. So as the robot is moving forward and laying down the metal, its head is also moving forward and backward in this perfect rhythm. This isn't some random vibration. It's a carefully engineered dance move. So why on earth does a wiggle fix everything? Well, the idea is actually genius. That constant motion basically stabilizes the chaotic pool of molten metal. It acts like you're constantly stirring it, spreading the heat out more evenly, and stopping that nasty backflow we talked about. The dream is to get those perfect, smooth layers, but now at super high speeds. It sounds great on paper, right? A simple little wiggle solves this massive manufacturing problem. But, the proof is in the pudding. Does this thing actually work when you put it to the test? Oh, you bet it does. The results are just wow. Look at this chart. It tells the whole story. It's showing track height deviation, which is just a fancy way of saying how bumpy the layers are. Low is good, high is bad. So, bar 1 is normal, slow speed. Nice and low, just what we want. Bar 2 is high speed with no wiggle. And yikes, the bumpiness shoots through the roof. That's our problem. But then look at bar 3, high speed plus the wiggle. And bam, the bumpiness drops right back down to where it should be. It's not just an idea, it's a total game changer. Okay, so the wiggle works. Awesome. But it turns out you can't just shake the robot and hope for the best. To get those perfect results every single time, the researchers had to figure out the exact right kind of wiggle. They had to find the recipe for success, the absolute sweet spot. And how'd they do that? With a ton of work. We're talking over 75 different experiments, tweaking every little variable you can think of. They took all that data and used it to create these incredible process maps. And really, you can think of them like a treasure map for engineers, showing them the exact path to a perfect print. What these maps do is show you exactly what to do and what not to do. There's a safe zone, that's the green area, where your combination of settings gives you smooth, beautiful, strong tracks. And then there's the danger zone, the red, and that's where you get all those nasty humps and defects. The goal is simple: stay in the green.
So, what did they figure out? What's on these maps? Well, for one, the size of the wiggle, the amplitude, is a huge deal. A smaller, tighter wiggle gives you more cycles, which distributes the heat better and gives you a smooth track. But if you use a bigger, wider wiggle, you get fewer cycles, which leads to uneven heating and, you guessed it, a bumpy track. Next up, they found this really delicate dance between the heat, that's the voltage, and how fast you're feeding in the metal wire. It's kind of like cooking, right? You need enough heat to properly melt the wire. But if you feed the wire in too fast for the amount of heat you have, you just get a big pileup of material, a gloopy mess. And get this detail is just wild. It turns out even the angle of the printing torch matters a lot. They found that a pushing angle, somewhere between 60 and 75 degrees, works perfectly. It creates uniform heat. But a pulling angle, anything over 90 degrees, causes all sorts of problems and can lead you right back to those defects. It's one of those tiny little details that changes everything. So, when you take all these discoveries, the wiggle, the amplitude, the voltage, the angle, and you put them all together, what you get is a clear, reliable playbook for the future of manufacturing large metal parts. The path forward is suddenly crystal clear. Step 1. Crank up the speed for productivity. Step 2. Turn on the magic wiggle. Step 3. Use those process maps to dial in all the other settings to that perfect sweet spot. And the result? You get a strong, smooth metal part built faster than we ever thought possible. And you have to remember, this isn't just some theory someone dreamed up. This is backed by serious, rigorous science. More than 75 detailed experiments prove that this works. So what's the big takeaway from all this? It's simple, and it's huge. That old nagging conflict between going fast and getting high quality in metal 3D printing, it's been solved. Thanks to a clever wiggle and some really careful science, we can now build bigger, faster, and better. I think what's so amazing is that this entire leap forward came from teaching a robot a simple back and forth motion. It really makes you wonder, doesn't it? What's the next small, elegant trick that's going to unlock another giant leap in how we build the world of tomorrow?